Hello everyone, in this video we are going to talk about real numbers. Let us start with natural numbers. The numbers like 1, 2, 3, 4 which are used for counting are called natural numbers. When we include 0 to the natural numbers, we get the whole numbers. And to these whole numbers, when we include the negative numbers as well, like -1, -2, -3, all the way up to minus infinity, we get the integers. Now there are some more numbers, for example 5/2. Now this is a fraction and we know that this is not an integer, it is not a whole number, and it is not a natural number. Numbers like this are called rational numbers. And there is a definition for rational numbers, that all the numbers which can be written in the form of p upon q, where p and q are integers. That means p and q should be among these. So p can be -3, -2, 1, 2, 3, any number or any integer, and q can be any integer. But there is another condition, that q must not be equal to 0. P can be 0, but q must not be equal to 0. Let us take some other examples of rational numbers. Let us say 10/11. So here p is 10, q is 11. Both are integers and we know that q is not 0. So this is a rational number. Similarly, -2/5 is a rational number because 2 and 5, where -2 is p, 5 is q, and q is not equal to 0. Similarly, we can write all the integers, let us say -4 as -4/1, where -4 becomes p and 1 becomes q. And we know here q is not equal to 0 and p and q both are integers. So we can say that this number -4 is indeed a rational number. We can do this for all the integers. Let us say 3, we can write 3 as 3/1, where 3 is p and 1 is q, and q is not equal to 0 as we can see. So we can say that 3 is also a rational number. So in conclusion, we can say that all the numbers that we have studied so far, which are natural numbers, whole numbers or integers, together they are called the rational numbers. Now moving forward, we have irrational numbers. Let us take an example of √2. We can write √2 as √2/1, but we know that in this case p is not an integer because √2 is not an integer. So what can we say about √2? We say that √2 is not rational, or we can say it is irrational. So what are irrational numbers? Numbers which are not rational, or numbers which cannot be written in the form of p upon q. So numbers which cannot be written in the form of p upon q, where P and Q are integers and Q is not equal to 0. So all the numbers which are not perfect squares, let us say 3, and we have 2, of course, 2, 3, 5, 6, 7 and so on. When we take the square root of them, so square root of 2, square root of 3, square root of 5, square root of 6 and square root of 7, we can say that all of these numbers are irrational. And definitely there are so many irrational numbers. Now let us move on to the main topic, which is the real numbers. So what exactly are real numbers? So when we combine all the rational numbers and the irrational numbers, we get real numbers. So all the numbers that we have studied so far in this video are all real numbers. Let us discuss a few more things before moving to the exercise. This person you can see is a great mathematician whose name is Euclid, and he gave a very important theorem in mathematics which is called the Euclid's division algorithm. So let us understand this algorithm with a easy example. Let us try to divide 21 by 3. So 3 can divide 21 7 times and we get 0 remainder. We'll also try to divide 22 by 3. So we get 7 again, but in this case we get 1 as the remainder. So this 7 in this case is the quotient and 0 is the remainder. In this case again 7 is the quotient and 1 is the remainder. Let us consider 21 as A and 3 as B. In this case 22 as A and 3 as B. We can also write this 21 as 7 into 3. So 7 into 3 plus the remainder 0, which is 21. And we can write 22 as 7 into 3. So 7 into 3 plus 1. Now we'll always notice one thing, and we already know it, that this remainder is never going to be bigger than the B. And this exactly is Euclid's division algorithm. So Euclid said that whenever we divide a number A with B, we get a remainder which is always less than B. I'll just repeat it with the example of this one. Whenever we divide a number A with another number B, we get remainder R such that this R is always less than B. But this R can be 0. Okay, so let us state this rule here. When we divide a number A by B, we get remainder R such that R is less than B. But we know that R can be 0. As we have seen here, R can be 0. So we can also write this as, For example, this 21 is A, is equal to 7 is Q, and 3 is B, and this 0 is R. So I can also write A is equal to QB or BQ plus R, and we know that this remainder it is always less than B. This remainder is always less than B, but it is greater than 0, but it can also be equal to 0. So we can say that this R is greater than equal to 0, but it is less than B. Let us talk about another important rule in mathematics, which is called the fundamental theorem of arithmetic. We'll understand this with a few examples. Let us say 12. We can write 12 as 2 into 3. So 2 times 2 is 4, and 4 times 3 is 12. And we can take any number, for example 15, and we can find the factors of 15. So 3 can divide 15 5 times, and 5 can divide it once. So 15 can be written as 3 into 5. And one thing we have to remember, that all of these numbers or all of these factors, they are the prime factors. So for this, let us understand what are prime numbers or what are prime factors. So those numbers which have only two factors. So we know that every number has two factors. For example, 3 has two factors, 1 and 3 itself. 5 has two factors, 1 and 5 itself. 6 has factor 1 because 1 can divide 6, 2 can divide 6, 3 can divide 6, and 6 can divide itself. In this case, we can see that 3 and 5 has only two factors, and the factors are 1 and the number itself. 1 and the number itself. So we call these kind of numbers as prime numbers. And numbers which have more than two factors are called composite numbers. So why these 3 and 5 are prime factors? Because they are prime numbers and they are the factors of 15. Similarly, 2 and 3 are again prime factors of 12. So the fundamental theorem of arithmetic says that every composite number like 6, 12 or 15 can be written as the product means the multiple, okay, the product of its prime factors. So for example, 12 can be written as the product of its prime factors as 2 into 2 into 3. 15 can be written as the product of its prime factors as 3 into 5. Similarly, we can write every composite number as the product of its prime factors. Now let us move on to the exercise. The first question we have is express each number as a product of its prime factors. So we need to find the prime factors of all these numbers. So what we need to do to find the prime factors, we need to write the number and draw lines like this, and we need to think of the smallest number which can divide 140. It should not be 1, it should be bigger than 1. So the smallest number we can think of right now is 2. So 2 can divide 140 70 times. Now again we need to think of the smallest number that can divide 70, which is again 2. 2 can divide 70 35 times. The smallest number that can divide 35 is 5. So we need to go first, we need to check with 2. We cannot divide 35 by 2, so we need to check for 3. 3 cannot divide 35. We need to check for 4. 4 cannot divide 35. So we take 5, and 5 can divide 35 7 times. And we know that 7 itself is a prime number, so there is no number less than 7 that can divide 7. So we take 7 here, and 7 divides itself 1 times. Okay, so 140 can be written as 2 into, so 2 into 2 into 5 into this one 7. So we can say that 140 can be written as 2 into 2 into 5 into 7. Okay, let us move on to the next part. So the next one is 156, and we have to think of the smallest number that can divide 156, which is 2. 2 can divide this 78 times, and to divide 78 again we can use 2. So 2 can divide this 39 times. Now 2 cannot divide 39. We can divide 39 with 3, and 3 can divide this 13 times. Now we know that 13 itself is a prime number, so we can divide 13 by 13 and we get 1. So 156 can be written as 2 into 2 into 3 into 13. The next number we have is 3825. We know that this number is not divisible by 2 because it is an odd number. So we can check divisibility by 3. So when we have big numbers like this, we can simply add up the digits of the number. So 3 plus 8 plus 2 plus 5, and check the divisibility by 3. So what do we get? 8 and 3 is 11, 11 and 2 is 13, and 13 and 5 is 18. So if the sum of the digits is divisible by 3, the number itself should be divisible by 3. So we know that 18 is divisible by 3, so 3825 must be divisible by 3. So 3 can divide this 1 and 2 and 7 and 5. So we get 1275. Now can we divide this number by 3? We'll again add the digits 1 plus 2 plus 7 plus 5, and we get 15. So yes, we can divide this by 3. So we get 4, 2 and 5, 425. Can we divide 425 by 3? 4 plus 2 plus 5 is 11. So we cannot divide this by 3, and we cannot divide this by 4. So we will take 5, and 5 can divide this 85 times. Again 5 can divide 85 17 times, and we know that 17 is a prime number, so 17 can divide itself 1 times. So we get the prime factors of 3825 are 3 into 3 into 5 into 5 into 17. Moving on to the next one, which is 7429. 7429. This number, for this number, the smallest number that can divide 7429 is 17, and 17 can divide this 437 times, and the smallest number that can divide 437 is 19, which can divide this number 23 times, and 23 itself is a prime number, so 23 can divide itself once. So for 7429, the prime factors are 17, 19 and 23, and we can write this number as 17 into 19 into 23. So whenever we have a number like this, there is no shortcut to find out the smallest factor. We will always need to check the numbers one by one. So we will need to check by 2, then 3, then 4, all the way until we find a factor. The second question is, find the LCM and HCF of the following pairs of integers and verify that LCM into HCF is the product of the two numbers. So before we start this, let us understand what LCM and HCF is. So LCM stands for the least common multiple, and for this we are going to take example of two numbers, let us say 12 and 16. The multiples of 12 are 12, 24, 36, 48 and so on, and the multiples of 16 are 16, 2 times 16 is 32, 3 times 16 is 48 and so on. So these are the multiples. Do you find any multiple which is common to 12 and 16? And the answer is yes. 48 is a multiple which is common to both. There is nothing else that we can see, but when we write more multiples of 12 and 16, we can find more common multiples. But 48 is the least common multiple of 12 and 16. So LCM or least common multiple of 12 and 16 is 48. Now let us talk about the HCF. What is HCF? HCF stands for the highest common factor. Now we can say that HCF is like the opposite of the LCM. First of all, we need to see the factors of the given numbers. Let us take the example of 12 and 16 again. So the factors of 12, so here we talked about multiples, but now we are going to talk about factors. So factors of 12 are 1, 2, 3, 4, 6 and 12 itself. The factors of 16 are 1, 2, 4, 8 and 16 itself. So are there any factors in common? Let us find out which are the factors in common. So we have 1 and 2 and 4 and that's it. So we have these three factors which are common. So what are the common factors? 1, 2 and 4. And which one is the highest common factor? The highest common factor is 4. So we say that the HCF of 12 and 16 is indeed 4. Now there is a interesting thing to note, and there is a formula which says that the numbers, for example, this is number 1, let us say, and this is number 2. The number 1 multiplied by the number 2 is the LCM multiplied by the HCF. So when we have 12 and 16 and we multiply 12 and 16, we get the same as their LCM, which is 48, into the HCF, which is 4. So let us check this. We can do it here. 12 into 16. So 6 2s are 12. We have carry 1. 6 1s are 6 and 1 7. And we have here 12, 2, 9. So we have 192, and we can check for this. 48 into 4, 4 8s are 32, we have carry 3, 4 4s are 16 and 3, 19. So we have 192 on both the sides. So we have verified that whenever we multiply the two numbers, we get the same as LCM into HCF. So now we'll move on to the exercise. The first question we have is 26 and 91. First of all, we need to find the LCM and HCF, and there is a rule, there is another trick to find out the LCM and HCF, which I'll be sharing now. So we have to write both the numbers separately, 26 and 91, and we need to find the prime factors of both the numbers. So let us start with 26. The smallest number that can divide 26 is 2, which can divide it 13 times, and 13 is a prime number, so 13 can divide itself once. For 91 we have 7, and 7 can divide this 13 times, and then 13 is a prime number, so which can divide it once. So we can write So we can write 26 as 2 into 13 and 91 as 7 into 13. To find the HCF, we need to take the common factors. So here we have only one factor in common. So HCF of 26 and 91, 26 and 91 will be 13. And to find the LCM, we need to take the common factor once, which is 13, and multiply this with the remaining numbers into 2 into 7. So the LCM will be 13 into 14, which is, when we do this, 14 into 13, 3 4s are 12 and carry 1, 3 1s are 3 and 1 4, and we have 14, and we get 182. So this is 182, and we need to verify that the LCM into HCF is equal to the product of the two numbers, which we can do here. So we need to verify that number 1 into number 2 is equal to the LCM into the HCF. So what is the first number here? 26 into the second number is 91, and we need to verify that this is equal to the LCM, which is 182 into the HCF, which is 13. So let us find out, and I'm going to check this in my calculator. So we have 26 into 91, which is 2366, and on this side we have 182 into 13, which is again 2366. So for this we have verified that when we multiply the two numbers, we get the result same as multiplying the LCM and the HCF. Let us move on to the next question. Let us see the second question now, which is 510 and 92. So we need to find the prime factors of 510 and 92. So we can divide 510 by 2 255 times, and we can divide this number 255 by 3, which is 85 times. We can divide 85 by 5, and we can do this 17 times, and 17 is a prime number, so we can divide 17 by itself one time. For 92 we can use 2, which will divide this 46 times. We can use 2 again, which will divide this 23 times, and 23 is a prime number, so 23 can divide itself once. And now we can write 510 as 2 into 3 into 5 into 17 as the multiple of its prime factors, and we can write 92 as 2 into 2 into 23. And when we take the common factors, we have only 2. There is no other factor which is common to both, so we can say that the highest common factor of 510 and 92 is 2. To find the LCM of 510 and 92, we need to take this common factor once and multiply this with all the rest of the factors. So 2 multiplied by 3 into 5 into 17, and here into 2 into 23. So we get 2 3s are 6, 6 5s are 30, 30 into 2 is 60. So this is 60 into 17 into 23, which is 23,460. Now let us verify that the product of the two numbers, which is n1 into n2, is equal to the LCM into the HCF. So in this case, n1 is 510 into n2 is 92, and this should be equal to 2 into 23,460. So when we do this, we get 510 into 92, which is 46,920, and we multiply these two, which is 2 into 23,460. This is also 46,920. So with this we have verified for the second question. Move on to the third one. Okay, the third one is 336 and 54. Let us write them here. 336 and 54. We can divide 336 with 2, and we can divide this 168 times. We can divide 168 by 2 84 times. We can divide 84 by 2 42 times. We can divide this by 2 again, which is 21 times. Now 21 can be divided by 3, which can be done 7 times, and 7 is a prime number, so 7 will divide itself once. 54 can be divided by 2 27 times. 27 can be divided by 3 9 times. 3 can divide 9 3 times, and 3 can divide itself once. So we can write 336 is equal to 2 into 2 into 2. So 1 2 3 4 2s into 2 into 3 into 7, and 54 is equal to 2 into 3 into 3 into 3. Let us find the common factors. So we have 2 common, and we have this 3 common. So we can say that the HCF of 336 and 54 is 2 into 3, which is 6, and the LCM of 336 and 54 is, we'll take 1 from these, so 2 into 3 into 2 into 2 into 2 into 2 into 2 into 2 into 7 into 3 into 3. And when we do this, we get 2 3s are 6, 6 2s are 12, 12 2s are 24, 24 2s are 48 into 7 3s are 21, and 21 into 3 is 63. So when we do this, 48 into 63, we get 3024. So now let us verify whether number 1 into number 2 is equal to LCM into HCF or not. So number 1 is 336 into the second number is 54, which should be equal to the LCM 3024 into 6. So when we do this, 3024 into 6, we get 18,144, and when we do this one, which is 336 into 54, we get the same 18,144. So with this we have verified the third one as well. Let us move on to the next question. In this one, we have to find the LCM and HCF of the integers by applying the prime factorization method. So let us start with the first one. We need to use the same method that we have used in the previous question. So we'll take the factors of 12, 15 and 21 for the first question. So the factors of 12 are 2 can divide 12 6 times, and 2 can divide 12 6 times, 2 can divide 6 3 times, and 3 can divide itself once. For 15 we'll take 3 can divide 15 5 times, and 5 can divide it once. For 21 we'll take 3 7 times, and 7 once. Okay, so we can write 12 as 2 into 2 into 3, and we can write 15 as 3 into 5, and we can write 21 as 3 into 7. Let us try to find the factors which are common. Now we need to look for factors which are common in all of these. So 3 is a common factor of 12, 15 and 21, and there is no other factor which is common. So we can say that the HCF of 12, 15 and 21 is 3, and to find the LCM of these numbers, we need to write this 3 once and multiply this with all the rest of the factors. So 3 into 2 into 2 into 2 into 2, then into 5 into 7. So by doing this we get 3 2s are 6, 6 2s are 12, 12 5s are 60, and into 7, which is 420. So the HCF is 3 and the LCM is 420. Okay. Now one thing we need to remember is that whenever we have three numbers like 12, 15 and 21, we cannot use the number 1 into number 2 method to find the LCM into HCF. So this can be used only when we have two numbers. So in this case we have three numbers, so we cannot use this formula here, and definitely in the question we do not have to verify anything like this. The next question we have is 17, 23 and 29. Let us find the factors of these three numbers. The factors of, okay, So as we can notice that 17, 23 and 29, these all are prime numbers. So they do not have any factors except 1 and themselves. So we can simply write 17 as 1 into 17. We can write 23 as 1 into 23. And we can write 29 as 1 into 29. Now what is common to all of them? There is only one factor which is 1 common to all the three. So we can say that the HCF of 17, 23 and 29 is 1. And what will be the LCM? LCM of 17, 23 and 29 will be 1 into, so 1 into 17 into 23 into 29. So multiplying with 1 gives us the same number. So we can write this as 17 into 23 into 29. So we can say that whenever we have HCF of two numbers as 1, the LCM will be just the product of the given numbers. So when we multiply these three numbers 17, 23 and 29, we get 7429. So let me write this with a darker color. So the HCF will be 1 and the LCM will be 7429. Okay, let us move on to the next one. So the next one is 8, 9 and 25. So let us write 8, 9 and 25 to find the factors. So 2 can divide 8 4 times and 2 can divide 4 2 times. 2 can divide itself once. 3 can divide 9 3 times and 3 can divide itself once. 5 can divide 25 5 times and 5 can divide itself once. So we can say that, or we can write it as 8 is equal to 2 into 2 into 2 and 9 is equal to 3 into 3 and 25 is equal to 5 into 5. As we can see that there is no factor which is common to 8, 9 or 25. So we can write this as, we can multiply all of them with 1 and we can say that 1 is a common factor. So in this case as well, the HCF will be 1 and the LCM will be, so whenever we have LCM 1, what do? We can just multiply the numbers, or we can check this using by multiplying the factors as well. So the LCM will be 2 into 2 into 2 into 3 into 3 into 5 into 5, which is equal to 2 into 2 into is, sorry, 2 into 2 into 2 is 8 into 3 into 3 is 9 into 5 into 5 is 25. So this gives us the multiple of the three numbers 8, 9 and 25. So when we multiply them, we get 1800. So the LCM will be 1800. The fourth question is, given that HCF of 306 and 657 is 9, find the LCM of 306 and 657. So for this, we do not need to find the LCM using the methods we have used before. Instead, we'll use the formula, which is number 1 into number 2 is equal to the HCF into the LCM. So in this case, we know that number 1 is 306 and the number 2 is 657, and we know that the HCF of these two numbers is 9 and we need to find the LCM. So we can also say that LCM is equal to, this 9 will go here in the denominator. So this is 306 into 657 upon 9. So when we do this, what do we get? So let me use my calculator for this. So we get the LCM of these two numbers as 22,338. The fifth question is, check whether 6 to the power n can end with the digit 0 for any natural number n. So let us first understand what this question says. It says that we have given 6 to the power n, and n is a natural number. That means n can take the values. So n can take the values 1, 2, 3 and so on. And whenever we replace this n with any of these digits 1, 2, 3, will it end with the digit 0? So we can just check this. First of all, let us put n is equal to 1. So 6 raised to the power 1 is 6. Let us put n is equal to 2. We have 6 to the power 2, which is 6 into 6, which is 36. When we put n is equal to 2, we get 6 to the power 3, which is 6 into 6 into 3 into 6, which is 36 into 6 is 216. Okay. Now, one thing we will notice is that this never ends with 0. This is always ending with 6, 6, 6. Even when we do 6 to the power 4, this will be 6 multiplied 4 times. We will get 1296, and this again ends with 6. And we can do this for any value of n, and we will always get 6. So we can say that 6 to the power n will not end with the digit 0. So we can write the answer that 6 raised to the power n will never end with the digit 0 for any natural number n. Okay, in question number 6, we need to explain why these numbers which are given are composite numbers. So one way of verifying is to find out the actual value of these numbers and then finding out the factors. If there are more than 2 factors, we can say that they are composite. There is another way which is easier than the one I just said, which is by taking the numbers which are common. For example, in this one, 13 is on both the sides of plus. So what I can do is I can take 13 common, and we'll have 7 into 11 into, I have taken 13 outside, so I need to put here 1 plus 13 is outside, so I need to put here 1 again. And the another number is, what can we take common here? So this is plus sign. On this side we have 5, on this side also we have 5, so we can take 5 common. So we'll have 7 into 6 into, in place of 5 we'll write 1 into 4 into 3 into 2 into 1 plus, instead of 5 we need to write 1 because we have taken 5 outside. So now we know that what's a composite number. A composite number has more than 2 factors, and we know that every number has 2 factors. What are the 2 factors? 1 and the number itself. But composite numbers have more than these 2 factors, so there is an additional factor. So in this case we can say that whatever this number will be, it has two different factors other than 1 and itself. One of the factor is this 13 and the another factor is this number. When you find out the value of this, you will get 78. So 13 and 78 are the factors of this number, or we can say this number. Similarly, 5 and this whole are the factors of this number. So we can say that the given numbers are composite. The given numbers are composite because they have factors, they have some factors other than 1 and themselves. So these numbers have factors other than 1 and themselves, that is why they are composite numbers. Hope you understood this. Let us move on to the next one. Now let us read out question number 7, which is, there is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? Let us first of all understand this with a diagram. Let me draw this ground. Let us say that this is the ground, and we'll assume that both Sonia and Ravi are at this point. So both of them, Sonia as well as Ravi, are at this point right now. So what is given to us is that Sonia takes 18 minutes. So Sonia will take 18 minutes and Ravi will take 12 minutes to complete one round of the ground. And what is given to us is that they both start at the same point. So they are at the same point and at the same time and go in the same direction. So they go in the same direction. After how many minutes they will meet again at the starting point? So after how many minutes? So once they start from here, after how many minutes they will start again? So we know that because Sonia is taking more time to complete one round of the ground. So suppose Sonia has completed one round in 18 minutes, Ravi will already have crossed this point after making the first round. Okay, so let us visualize this. So let me write here round 1, okay, round 2 and round 3. Okay, so this is Sonia and this is Ravi. So Sonia completes the first round in 18 minutes. She will complete the second round in 36 minutes and third round in 54 minutes. Let us talk about Ravi. He completes the first round in 12 minutes, second round in 24 minutes and the third round in 36 minutes. So we will notice one thing here, that when Sonia completes second round after 36 minutes, Ravi has completed the third round. So we can say that after 36 minutes, Ravi will have completed 3 rounds. So Ravi will be here, and after 36 minutes, Sonia will have completed 2 rounds and Sonia will also be at the starting point. So the answer is they both will meet at the starting point. They both will meet at the starting point after 36 minutes. Okay, and there is another way of finding this out with respect to what we have learned in this lesson. We can also take the LCM, the least common multiple of 12 and 18. So we can write 12 and 18 separately, and we can find out the least common multiple. We can divide this by 2 to get 6, 2 to get 3, and 3 to get 1. We can divide 18 by 2, get 9, 3 to get 3, 3 to get 1. So 12 is 2 into 2 into 3, and 18 is 2 into 3 into 3. So what will be the LCM of the two? So 2 is common and 3 is common. So the LCM will be 2 ones and 3 ones into this 2 into this 3, which is 2 into 3 is 6, 6 into 2 is 12, and 12 into 3 is 36.